Hello guys, this is Code and Code and this is the 11th lecture of this number theory series, and in this lecture we are going to solve this problem modular GCD taken from Codechef. So the problem is you are given three integers a, b and c, and you have to calculate the GCD of two numbers where first number is a raised to power n plus b raised to power n, and the second number is absolute difference of a and b. And in the bracket it says that GCD of 0a is equals to a. If you are following this series and you have taken the lecture where we have talked about Euclidean division algorithm, so in that lecture we have seen that okay, GCD of 0a is actually a. So this is not something new for us. Since the answer can be very large, so we have to print it modulo 10 to the power 9 plus 7. If you look at the constraints, so constraint says there can be as large as 10 test cases, and a, b and n can be as large as 10 to the power 12. And it is also given that a is greater than or equal to b. So their absolute difference would be a minus b. So if we look at the test cases, there are two test cases. In first one, it is given 10 1 1, that is a and b are 10 1 and n is 1. So the first number would become 10 raised to power 1 plus 1 raised to power 1, and the second number would become 10 minus 1. So 11 and 9, the GCD is 1. The second argument for second test case, we have a, b as 9 1 and n is 5. So the first number would become 9 raised to power 5 plus 1 raised to power 5, and the second number would become 9 minus 1. So you see the first number becomes very large, it's like 59,050, and the second number is 8. GCD of both of them is 2. Now if you remember Euclidean algorithm for GCD, we know that we can calculate GCD of two numbers in log n time, right? But the problem here is that to calculate GCD of two numbers, we would pass two integers or long int into that function, and that would return GCD. But the problem is the first number is going to be very large. Reason, n can be as large as 10 raised to power 12. If you calculate 9 raised to power even 100, that is going to be a huge number. And if you see 9 raised to power 10 raised to power 12 is going to be too large. It would be that much big that even some libraries like in C++ Boost library, or in Java the big integer library, even those would not be able to store that big number. I'm talking about integer representation. 9 raised to power 10 raised to power 12 would be such large number. If you can't even store those two numbers, how you would be passing those two integers into the GCD function? That brings us to a challenge that we can't use Euclidean algorithm to calculate the GCD, because we are not able to store a raised to power n plus b raised to power n, because a and b itself are like 10 to the power 12, and calculating those numbers raised to power 10 to the power 12 is going to be very big number, which clearly shows us that we cannot use Euclidean algorithm to calculate their GCD. We have to use some other algorithm or some other way, or we have to derive some algorithm and use that to calculate GCD. So approach of this kind of question is something like this, even if some problem of this kind appears in the future. So if you need to calculate GCD of two numbers x, y, where x is huge and y is smaller as compared to x, or y is smaller, which can be represented in integer or long int, then we can find first of all potential GCD candidates, and then we would apply modular arithmetic to find GCD. Now see what is the difference. Usually we would use Euclidean algorithm to calculate GCD, but in this case first we would find the potential candidates for GCD, and then we would use modular arithmetic instead of Euclidean algorithm to calculate GCD. Let me show you how and what are potential candidates. Suppose the question was this is 4 into 10 to the power 20 roughly. roughly it is 4 into 10 to the power 20, and long int can store at max 10 to the power 19. It can't go beyond that, so it is even beyond the reach of long int. So if you have two numbers like this and you have to calculate GCD, then use the second argument, which is smaller. In this case, the second argument, that is absolute difference of a and b, can be at max 10 to the power 12. Reason? Since the second argument is a minus b, so it would attain its maximum value when a is maximum and b is minimum. Maximum a can be 10 to the power 12, minimum b can be 0. So the second argument can be as large as 10 to the power 12, not beyond that. So the potential candidate we can calculate from second argument from a minus b. And potential candidates are going to be all the divisors of this second argument. And the divisors of 90 are 1, 2, 3, 5, 6, 9, 10, 15, 18, 30, 45 and 90. Why these are potential candidates? See, the definition of GCD is that it is greatest common divisor of both of the number. That is, it is the greatest number that can divide both the number first and second. Of course, the GCD first have to be a divisor of both of the numbers, right? Then we would see whatever is the divisor of second number, that would be our candidate, and the one which can also divide second number, and we have to maximize that number. First of all, we would find all the divisor of second number which we can find, and then from that number, all the numbers that divide the first number, which is very large, among all that number we have to choose the maximum one, and the maximum number would be their GCD. Now since the second argument a minus b is going to be as large as 10 to the power 12, and we have seen in the first or the second lecture where we were studying about prime factorization or primality test, we have seen that we can derive the divisors, we can find the divisors of a number in square root of n time. That is, the maximum number can be 10 to the power 12, so square root of 10 to the power 12 would be, in worst case, 10 to the power 6. So we would be running a loop till 10 to the power 6, which is okay. So in square root of n time, we are able to generate all the divisors of second element. Now we have the divisor of second element. Now how to check whether the current divisor or whether a candidate divides a raised to power n plus b raised to power n as well or not? Again, the same problem occurs. We can't save a raised to power n plus b raised to power n in a variable, right? So checking whether that number is divisible by one of the candidates or not would be difficult. But since we have studied modular arithmetics, so after finding all the candidates, all we can do is, we know it is difficult for us to calculate a raised to power n plus b raised to power n, but since from the previous two lectures 9 and 10, we have seen that we can calculate a raised to power n modulo some number. This is modulo exponentiation, and we have studied it in lecture 9 and 10. So we know we can't calculate a raised to power n plus b raised to power n, but we can calculate a raised to power n modulo d, where d represents the current potential candidate divisor, right? So we can't calculate a raised to power n plus b raised to power n directly, but we can calculate a raised to power n modulo d. Now what we are going to do is a divisor. We would run a loop from first to the last divisor, that potential divisor, and then we would calculate a raised to power n plus b raised to power n modulo d. If a raised to power n plus b raised to power n modulo d comes out to be 0, which means a raised to power n plus b raised to power n is divisible by this divisor, and we would find the maximum such divisor which leaves 0 remainder when calculated for this expression. But the same problem is again, a raised to power n plus b raised to power n would be beyond our reach. But in the lecture 9 and 10, we have also seen that a raised to power n plus b raised to power n can be calculated as a raised to power n modulo d, which we can calculate, plus b raised to power n modulo d and whole modulo d. So calculate this expression, we can calculate this. All we have to calculate is a raised to power n modulo d plus b raised to power n modulo d, and then take their modulo finally. If this expression comes out to be 0, that means d divides a raised to power n plus b raised to power n as well. So we would find the maximum d which leaves 0 remainder, and d is actually this, the potential candidates. So it may sound a little confusing if you haven't seen the lectures 9 and 10 in which we have talked about modular arithmetic. Just go there and watch that lecture, because now I'm going to code this problem and solve it, so that you have a better understanding what's going on. Come on, boy. Now this should be good. We would write each and every function by yourself. So first of all, I'm taking a, b, n and t long int integers. LLI is long int, right? Or instead of writing long int everywhere, I've just taken the preprocessor directive. So I've taken 4 variables a, b, n and t. T is test case. After reading test, in each test cases we are reading a, b and n, and then finally GCD function would return GCD of basically it gives the answer of each test cases. It would give us GCD of a raised to power n plus b raised to power n comma a minus b. So we have to design it right here. The first question, the first condition that you should check is whether a is equals to b or not, because if a is equals to b, then a minus b would become 0. In that case, the result would be a raised to power n modulo 10 to the power 9 plus 7, because now since the second argument becomes 0, answer would be the first argument. First argument is a raised to power n plus b raised to power n. So we have to calculate a raised to power n plus b raised to power n, and that we would return it modulo 10 to the power 9 plus 7, right? So a raised to power n modulo 10 to the power 9 plus 7. You can define 10 to the power 9 plus 7 as constant. I have taken it as hash defined preprocessor directive. I always use it as mod. So this was return this would return a raised to power n modulo 10 to the power 9 plus 7 plus b raised to power n modulo 10 to the power 9 plus 7, and finally after that again take their sum, add them, and find, apply modulo operator again, and finally return a raised to power n plus b raised to power n modulo mod, that is 10 to the power 9 plus 7. If a is equals to b, this would be our result. Otherwise we have to generate we have to take let me write it as candidate. Initially the candidate would be 1, I is equals to 1, I into I is less than equals to n, I plus plus. This is what we are doing. We are running a loop till square root of n, and this loop is going to test all divisors of number. Yeah, we have to find all the divisors of a minus b, right? Because the second argument would be a minus b, and we have to find all the divisors of a minus b. That would be our potential candidates. So if I divides a minus b, that is if I divides a minus b, then it's then this is one of the candidate divisor, and if this is candidate divisor, what we have to do, we have to calculate the a raised to power n modulo d plus b raised to power n modulo d. If that is 0, then this is one of the candidates, can be one of the candidate GCD, one of the GCD candidate. We will calculate power a raised to power n, but this time modulo d. And why is that so? Because as explained earlier, we would calculate, since we have found d is current divisor, I is current divisor of this number, right? So we have to see whether a raised to power n modulo d, which is I in this case, plus b raised to power n modulo I modulo I leaves 0 remainder or not. If it leaves 0 remainder, that means this can be the GCD, and since we have to find the maximum number, because that would be the maximum divisor of both the number. So I've calculated a raised to power n modulo I plus b raised to power n, and yeah, remember the power function we have to write it down ourselves, so don't worry, we would write that ourselves. So what is this? This is a raised to power n modulo I plus b raised to power n modulo I, and then finally modulo I, since I is the current candidate. If temp is 0, that means I divides a raised to power n plus b raised to power n. In that case we would update candidate to be maximum of candidate comma I, because I is the current divisor. Now again, temp is equals to remember, if you are following from the lecture where we have talked about prime factorization, there we studied about pairs, divisor pairs. If I divides a number n, then n by I also divides n. Take an example of 12. Since 2 divides 12, so 12 by 2, that is 6. 6 also divides 12. So the second divisor would be n by I, right? So we also have to test for, let me just copy, we also have to test for n by I. We have tested for I, now we would test for n by I, and that is number by I. What is happening here is that since the I divides number, so I is one of the divisor of num, and we are checking whether it also divides a raised to power n plus b raised to power n or not. If it divides a raised to power n plus b raised to power n, then its modulo a raised to power n modulo I plus b raised to power n modulo I whole modulo I would be 0. So if it is 0, that means it is one of the candidates, so I am updating the candidate because we have to return the maximum candidate. Now since I is a divisor of a number, then n by I is also a divisor of that number. So we have tested for I, now we would test for n by I. So I am checking for a raised to power n modulo n by I plus b raised to power n modulo n by I, then whole modulo n by I. If again temp is 0, which means n by I is also a candidate. I don't know whether I'm writing the right spelling or not. And finally return our candidate. What we are doing here, from 1 to square root of n we are going, because we know till square root of n we can find all the divisor of n. So if n num is divisible by I, which means we have to test for a raised to power n plus b raised to power n modulo I. That is what we are doing here. If temp comes out to be 0, which means I divides both the numbers num and a raised to power n and b raised to power n. So we would update candidate to be max of candidate comma I. Again, if I divides a number num, then num by I also divides number num. So we have tested for I, we are now going to test for num by I. So now we are testing for a raised to power n plus b raised to power n modulo num by I. If temp is 0, then num by I is also a candidate, and we are again maximizing candidate. And finally we are returning the maximum candidate. Now the power function. You remember this is while n, that is while n is greater than 0, and this is nothing but binary exponentiation function, and now we are using it exponentiation with modulo, or basically modulo exponentiation. Now we know what we do. If n is odd, what we do result is equals to result into a, and then we do n minus minus, result is equals to result into a, and n minus minus, else we do a is equals to a into a, and n divide equals 2, right? And finally we return result. But this time, since we have to take it modulo d, so whenever you are going to do this, you do result modulo d into a modulo d and final modulo d, and minus minus, and here we are doing a into a, so we would do a modulo d into a modulo d and final modulo d, and everything seems good. Let's compile it and hope we don't get any error, which is highly unlikely because I always get errors. Well, there was so this is the problem. Modular GCD taken from Codechef. Let me just do this. So there are two test cases. 1011 answer is 1, 915 answer is 2. So we are getting the right answer till now at least. Let's copy and paste the solution. I don't know whether we'll be getting a right answer or wrong. Though I have solved this, I always solve the problem before making an editorial, of course, so I don't waste much of your time while solving errors and recording. See, wrong, there are some error. I was just worried about it. So if a is equals to b, we have to return a raised to power n modulo 10. Oh, sorry, final candidate modulo m 10 to the power 9 plus 7, because the question it is said, it is already told that you have to return the result modulo 10 to the power 9 plus 7, and that is what we were forgetting here. So we would take it modulo 10 to the power 9 plus 7 and then finally submit, and hopefully this time we don't get an error. Or yeah, wrong answer. Whew. I hate this. I hate waiting. Cowboy. This is second time and this really pisses me off. So if n is odd, result is equals to result into a, which is good. Otherwise a is equals to a into a, and then finally return the result a raised to power n modulo d, which is good. If a is equals to b, then we have to calculate a raised to power n modulo mod plus b raised to power n modulo mod, finally mod, and we have to return this, of course. Otherwise candidate is 1. Starting from 1 we are going till square root of n. Oh, sorry, we don't have to go till square root of n, but we have to go till square root of number, because we are finding the divisors of number, not n. That was the problem. How can I make such a mistake? Just imagine doing the same mistake on code forces and what would happen with yourself. Oh come on. Because with each wrong submission you get a penalty of like 20 or 30 minutes. This time should be correct, and sorry for the errors. All of them were just typo. Yep, we finally get an SE, and sorry for those errors. So we solved the problem modular GCD, and we made some mistakes. Just remember not to making the same mistake yourself. So what we did to calculate a raised to power n plus b raised to power n comma a minus b GCD of these two numbers, first we would check whether a and b are equal to each other or not. If both of them are equal, then a minus b would result into 0, and we finally have to return a raised to power n plus b raised to power n modulo 10 to the power 9 plus 7, and mod is actually 10 to the power 9 plus 7, right? If they are not, then candidate would be 1, and then we would calculate the number and a minus b, and then we would generate all its divisors. If num is divisible by I is divisor of num, and then we would check whether I is also divisor of a raised to power n plus b raised to power n. How we can do that? We can do that by applying modular GCD or modular exponentiation. If a raised to power n modulo I plus b raised to power n modulo I and then whole modulo I is equals to 0, that is I is also a divisor of the a raised to power n plus b raised to power n. So I is basically a candidate. If I is candidate, we are maximizing the candidate, so candidate is equals to maximum of candidate comma I. One more thing, if I is a divisor of num, then num minus I is also a divisor of n. So we are doing the same thing, checking whether num minus I also divides a raised to power n plus b raised to power n. If it divides, then we are again maximizing the candidate and then finally returning the candidate modulo 10 to the power 9 plus 7, because it is said in the question that we have to return result modulo 10 to the power 9 plus 7. And this function, the power function, this is modulo exponentiation. This is basically improvisation of the function that we've written previously, which is binary exponentiation. We simply replace all the multiplication with mod. We replace all a into b to a mod d into b mod d and then whole mod d, and finally return the result. So this was all about this problem. Thank you guys for watching till the next video drops. So bye.